Hello and welcome back to Calculus 1, section 2.7 on the precise definition of a limit. How ironic, right? At the end of the chapter, we get the definition for something that we have been using the whole chapter. But that's actually what happened in the history of the math development. The derivatives and integrals were already in use, and then 100 years later, limits were defined. So, what is the precise definition of a limit? Here it is. And you better know the statement, right? So, assume function f of x is defined for all x on some open interval containing a except possibly at a. So remember how limits do not require you to have a value at the point? That's the statement possibly at, except possibly at a. So this is the intro, and now we say limit x approaches a of f of x is equal to L if for any number epsilon larger than 0 there exists a number delta larger than 0 such that f absolute value of f of x minus L is less than epsilon whenever 0 is less than x minus a less than delta. So before you freak out, epsilon and delta are Greek letters that are equivalent to our E and D. These are the lowercase. So I'm talking about Greek letters epsilon and delta. Those are just lowercase e, lowercase d in Greek alphabet. The rest of the symbols you know. Epsilon and delta are extremely small numbers. They can be as small as you need them to be, as you want them to be. We did talk about earlier during the break about the nanometer scale and so on, and the width of the atom and so on. That stuff is very small. We cannot see atoms. We cannot construct the devices to see atoms. That's how small they are. But we can still find much smaller numbers than atoms. So when I say epsilon, when I say delta, mathematically we can make those values as small as we want. Atom size is 10 to the negative 15. That's very small, 10 to the negative 15. There is nothing in the books that says that you can't have 10 to the negative 100, 10 to the negative million. That's far smaller than 10 to the negative 15, which is the size where the atoms live. So epsilon and delta are extremely small numbers, and you can make them as small as you want. Now, here are the two graphs. Graph number 1, we have some function f of x, and I'm going to pick a value here, which is my A, which produces the limit L. Now, I'm going to place A minus delta on the x-axis, which is a little bit to the left of A, and I'm going to place A plus delta a little bit to the right of A. Note that I'm using my Romeo and Juliet code. This translates into L plus epsilon and L minus epsilon on the y scale. So epsilons go with y and deltas go with x values. What I created is a tube around the black line, which is the width of delta in the domain, and it's the width of epsilon in the range on a y. Now I need you all to look at the screen, because I can't do this any way other than this. So look, as the red line and the blue line with the on x-axis, as they squeeze towards the black line, because we are approaching A, x goes to A. X can be on this side that goes to A, x can be on the blue side going to A. Anyway, when x goes to A, you are squeezing into A. As these blue and red squeeze towards A, they're gonna squeeze towards L. Do we all see that squeeze happening? Yes. Right? So the squeeze happens at the same time. As I squeeze here, it squeezes there. If I squeeze here, it will squeeze there, because they're all connected, right? So the idea of the limit is that squeeze, and that squeeze is the approach. So as my x that could be on the red side to the left, or on the right side, the blue, as the x approaches the black value A, which is what I care about, you see that they approach L, and that is what the limit. Now, we did that one-sided limits and all that cool stuff earlier, and this is what it means that the limit exists and the limit is L, because when we squeeze on x-axis, everything collapses into L on y-axis, making it so that the limit x approaches A from both sides of f of x give us L as the answer on the y. Remember what I said? Limit is a fancy way to compute y value. You got your y value. It's called L, right? The second image, and our final point that we are making for this lecture, is going to be your beloved 1 over x. And now I'm going to have my A at 0. I am going to get the delta, A minus delta red, which gives me the value on the y-axis. And then in blue, I have A plus delta. What can you tell me about red and blue y values as I squeeze x? They are going to infinitely diverge, right? If I go and I cut delta into, remember, you can make delta as small as you want, right? So that means I'm going to use smaller delta, which means I'm going to be closer to A. So if I use smaller delta, and I use smaller delta on the red side, do you see what happened? They are further apart. Remember that the limit they have to meet at L. Otherwise, suicide is the answer for Romeo and Juliet immediately, right? So we want them to meet. So as I squeeze, it goes opposite ways. It doesn't converge to a point. This is the definition for limit does not exist, because they do not converge to same L value. So in this case, limit f of x dne, because the y value is not converging into the same. The f of a plus delta, f of a minus delta, they do not go towards the same. So you see that the other argument that you can also make is that your epsilon needs to be extremely small, right? You see that your epsilon over here is going to be a huge number. Millions, billions, trillions, right? As you start calculating. Because think of the calculation 1 over x when x is 1 over 10 to the negative 6. Well, the answer is 10 to the 6, right? And 10 to the 6, that's a million. I need that to be extremely small, not to be 10 million. Million. All right, so that's the idea of the limit. You have the precise definition, which gives you this in words. Technically, it tells you that the function exists and that you are looking at the point A, which doesn't necessarily need to be here, like in our second example. And then it tells you that the limit exists if you are able to pick epsilon and delta such that when you subtract f of x and L, right, the difference between the two is smaller than epsilon whenever x minus a is smaller than delta. That's the squeeze. You squeeze here, it squeezes there. And that's just a mathematical way to show, and this definition is about 200 years old. So welcome to being 200 years behind current mathematics, right? But that's okay. We're going to catch up very quickly. By the time you are in Calc 3, you will be in 1800s already. So differential equations, and then linear algebra is already at the cusp of 1900s. So
when do you get to
keep pushing.
What's that?
Oh, that's the second postdoctoral degree.
Okay.